All right, so let's make a start. If everyone can please take some seats. There is some small spare seats down the front, and we'll kick off this session. For those who weren't here earlier, my name's Alex Campbell. I'm chairing the session, and the session sponsor today is SRK. Our first presentation today will be presented by Rod Hocking and Chin Zhang, and the paper is entitled Carrapateena Block Cave Mine Design and Planning, the Feasibility Study.
Big welcome to the people I haven't met before, which is probably about 6 of you. Lovely to see everyone here in Adelaide. So I'll be leading off the presentation to talk about the feasibility study and the mine design planning for Carrapateena. This is just a slide to talk about forward-looking statements for those people who are interested in that. Please read very quickly. And now we'll talk about Carrapateena. So Carrapateena is on Kokatha land, about 500 kilometres north of where we are today. And it's been through a number of iterations in the planning cycle through to operations today of the sub-level cave. Previously, we had 2-level block cave design, which we then transitioned to a single SLC. And this work is then looking at the expansion project for Carrapateena, which was delivered about the same time as we were ramping up Carrapateena, which was looking at mining a sub-level cave at a block cave beneath it. So it was a little bit of a unique opportunity for the study team. And I'll just shout out to all the people involved at Carrapateena. Like it really does take a village to do the planning for this work. So shout out to everyone who's been involved so far and those coming forward as well. So we talked about the sub-level cave. We did the work. We found significant value by replacing the bottom level at the SLC with the block cave. And that's driven almost entirely by the ore body. So values driven by increased production rate, higher grades at the lower part of the block cave, and also the low operating costs. And we did a lot of work around the sequencing of the cave. So our plan was to do the higher grade block cave 1 and then a lower grade block cave 2 adjacent to block cave 1. And that was done by doing some fairly detailed Hiller value type analysis. Hiller value is a process that's been set up for a number of different mining methods originally by Barry Hall and the AMC team. It's something that we did to look at where the best RL for the footprint, the best production rate, and also basically the size of the footprint. So we're basically trading all those off, looking at different metrics and getting the board guidance of what they were most interested in. And at the time, the decision was made to go after a 12 million tonne block cave footprint with a 70,000 square metre extraction level for BC1, followed by an adjacent design on BC2. I'll now hand over to Chin, who wrote most of this paper.
Thank you, Rod. Okay, I'm going to take you through the mine design schedule. Firstly, the extraction level design. As you can see on the pictures, we are using the LTNT layout in the design. As it's having a comparatively larger pillar and also easier to develop based on the previous experience. And draw point location is in consideration of the economic value, meaning the draw point MPVs and the geotech constraints, which is trying to avoid the any unfavorable geotech pillars or step changes on the shape. And the draw point space is defined as 32 meters times 22 meters. And that is not only based on the evaluation of the ore recovery to make sure we have interactive draw, and also the stability. A slightly larger pillar can help the stability for the life of the mine, for sure. For the material handling system, we have an footprint primary crusher located at the north of the footprint. The tip of the crusher is at the same level as the draw point, so the loader can take the ore from the draw point and travel to the tip and dump into the crusher directly, and there is no secondary or handling requirement. For the ventilation, the design is having the fresh air supplied from the southern side of the footprint, and it's in the same direction as the loader tramming direction, and the dusted air is exhausted through the return air rides before the dust reach the crusher. This is mainly in consideration of that the southern part of the extraction drive could still be used for other mining activities such as secondary break, service work, or road work, while the northern draw point can be bogged by the loader, so reduce the downtime of the extraction drive. The water drainage of the design, water is drained away from the crusher. This is make sure that the critical infrastructure is the last thing to get flooded. It also has advantage to, we can also take the advantage to use the extraction driver as the extraction level as the surge capacity. Undercut level, it's 70 meters above the extraction level. In the feasibility study, the advanced undercut strategy choosing based on the most updated ore body knowledge at the time. As most of you probably already know, advanced undercut strategies to undercut is fired in advance of the draw point drive and the draw bears. So the draw point drive development and draw bear firing are done under the stress shadow. The Big W undercut drill and the blast design was applied in feasibility study as it can provide a larger pillar, so which again provide better stability for the life of mine. We designed the ventilation drive on the same level as the extraction drive, and the small ventilation was developed to link to send the air, fresh air from the southern end down to the extraction level, and then the used air was exhausted up back to the undercut level from extraction level. The ventilation system design. We have, as there is an existing operation, SRC operation, so some winterize already established. While we were put the block cave at the bottom, we figure out that due to the cave establishment of the block cave, and also the SRC need to keep up the tons to feed the mill. The existing wind system of SRC actually cannot supply the air required for the block cave. So the decision was made to set up a new independent wind system for block cave. The wind requirement is assessed based on like equipment, height, model, random control, dust control, height, and other contamination underground. As you probably know, for the block cave, during the cave established period, the higher air volume is required, as there are more headings need to be supported due to the development and production firing activity, while the air requirement reduced at the steady states, while only bogging and secondary breakage are the main activities on extraction level. We also did some production simulation to check what fleet require. to meet the production rate. Some high-level summary here. We tested the multiple sides of the loaders, and we also analyzed the electric loader versus diesel loader performance. This gave us opportunity to actually analyze interaction at tips, and some scenarios we run, we actually need interaction in the drive itself. And also it has interface with material handling system, so we can actually simulate the underground operation as a whole system from the draw point all the way to the surface. Some initial results showing in the table shows the diesel loader that payload with 21 ton can meet the production requirement. While the biggest electric loader on the market tested was 18 ton. If we only have one loader per drive, it's not going to achieve the production rate. So we gradually increase the number of loader in the drive and find out that we need at least 11 18-ton loaders or 13 14-ton loaders. My previous colleague Scott and Colin from Polymesium will have more detailed, has a paper to describe more details about the simulation work later on. Mining scheduling. There's just some very high level brief to highlight like one key thing for the scheduling is the transition from the SLC to block cave. Because during the block cave establishment, the production need to come from the up SLC level. With the block cave propagate, and the seismicity gonna move up, and the it's gonna start impact the SLC production. So we really need to make sure from schedule point of view, the SLCs need to be seized when it's no longer safe to access, or we no longer need it to supply the to meet the production rate. So the mine schedule is developed to maintain the continuous ore production during the block cave ramping up and the SLC ramping down. And the picture showing that when in the feasibility study schedule, when the SLC stops, the block cave cave height is still quite a big distance away from the SLC level. So SLC level mining activity can finish before the geotech connection between two caves. While in execution, the cave growth and the seismicity response will be monitored to make sure a timely decision can be made to cease SLC operation. This is all I have on the slides. If there is any questions. Thank you.
Thanks, Jen. We do have time for one or two questions. Denver down the front here.
Just your the table showing the electric loaders, the jump up in the number of loaders compared to the difference between 21 and 18. I just noticed that it was a little bit disproportionate. Have you got any comments on that? Like about, I think it was
Simplistically, Colin's going to present on that.
Okay.
So I think let's not bring that out.
Another question?
Hi guys, great presentation. I was just interested in more so clarification with the ventilation circuit. So looking at that, that was I'm assuming the declines there is conveyor through to the bottom of the block cave, or is that trucking? And was that a neutral ventilation circuit down to the sub-level cave, and then it becomes fresh air below that?
Which one are we talking about this one? So the declines for that, you got parallel declines. So you basically got the ability to intake and exhaust. The vent staging does change through the life of the mine. And I'm pretty certain you'd need to put in secondary, like pushing vents to get the vent in the extraction drives to balance.
All right, one more question.
Just a quick one. How big your vents are then?
How big are
Vents are, the shaft.
the shafts?
How big for the ventilation?
5.5.
Excellent. Well, let's leave questions there. Please thank both our speakers. All right, our next presentation today is Chris Brown from CMOC. Today he's going to be presenting an iterative design and schedule approach to the E22 block cave project and production planning at CMOC North Parks, a case study.
Yes, working. All right. I just want to say, look, thank you for everyone for attending today. And I'd like to thank all my colleagues that have helped creating the work that's being presented in this presentation today. So to get things started, our problem was scheduling a block cave is a cumbersome process. If any of you have had the fortune to be given the task of using PCBC, creating a schedule, and then taking that through to production planning, you'd be well aware of all the inputs required and the avenues for errors that can introduce. To top that off, it's difficult to determine if your development, your production is aligned because there's a disconnect in the scheduling tools you're using. On one hand, you have PCBC creating a production plan, and on the other side, you've got perhaps Desweek, which is what we use, or maybe another software package to produce a development schedule. So we're using quite specialized scheduling software to create these outputs. And then unfortunately, we take all that work and throw it away by putting in Excel and running our plans out that way. It's prone to errors. It's probably caught everyone in the room. I know it certainly caught me. And the other challenge is it's not as simple as just going off the shelf and buying a software package that's capable of putting production with development scheduling. So we've attempted to address that issue. Objective was to present how we've gone about fixing that issue. So the key steps for us was to link the outputs of PCBC with our existing scheduler package, which happens to be Desweek. We want to have continual feedback from all of our design decisions and have that go back into our production reports to make sure that we're having an achievable plan from the very start. We want to account for all material movement. So a key area for this would be bogging the swell or mucking the swell from an undercut firing and aligning that to where that should come out of your PCBC schedule. And furthermore, because we have Desweek, we have schedules for all of our other caves. We have schedules for our open pits. Why not schedule it all together in one place? So here's the process that we've followed. We start by defining our inputs and complete a footprint finder. So there's been a lot of work on that already, so I won't go into that today. And then we progress through draw point selection, our PCBC schedule. We then want to confirm that what that's told us is achievable with some capability modelling. We then want to put a mine design to it and finally schedule a development out. It's here that the first point of iteration starts for us, where we look at different drawbell sequencing as to where that's achievable and what can we do with it going forward. And once we've done that an appropriate number of times, we know that we should have an integrated mine plan for line production and development. So with our draw point selection, the picture you'll see will have a series of red crosses and green crosses. The green crosses happen to be the E22 footprint. There's 154 of those, and the red ones happen to be the excluded draw points. And you may ask me, why would you include the excluded draw points in the picture? And that's just a scheduling trick with PCBCs. If you delete those, you ruin your opportunity for different optimization, and it tends to cause issues with harder draw calculations. We then carry forward into PCBC. And it's here that we want to track our mining inventory for our cave. So the picture beside is a typical example of a smaller sort of cave like we'd have at North Parks, where we have a series of ramp up, a nice flat steady state production period, and then finally draw point closure. For the purposes of the work today, the impact we can have on the ramp up stage for E22 would be the scheduling of draw points, as in how many and when they occur, the initiation point in the cave, development paths, site production rate curves, and draw strategies. So here we have some cave modelling actually made by Alex for us. And this shows that our initial sequence was to start in the eastern side of the cave. So the picture shows pointing northwards and then progress in an outwards northwestern direction. It was found that this is an achievable schedule, as in it would break through and you could make a cave out of it. But there are some drawbacks, which will be listed in the next slide. So that modelling identified that it'd be slow and intermittent and potentially unreliable cave progression. And this is because it was quite a narrow footprint geometry. So remembering that putting it in this position was in order to bring our schedule forward as fast as possible. Because it's the closest to our access and perimeter drive, it makes sense to start in the first point from a mine planning point of view. But then the geotechs come back and say, oh, hey, that's not a good idea with your cave. It was comforting to know that despite these capability issues, the cave would still form. And so we're confident that, yes, this is a good state to be in the project, but we'd like to do it better. So you can see in the picture in the left, the preference of material coming in on the eastern side and the slow initiation on the western side. To combat this, a chevron sequence was developed, as you can see on the right, starting in the centre of the cave closest to the crusher. It also has the benefit for our ore body of being in the high grade portion, so a little bit of a win-win for us. From here you can see where we've scheduled our undercutting, and without going too much into design, there's another presentation later this week. We have an advanced undercut path and we've applied a schedule to it. So we can see with the constraints applied with how many drawbells we're capable of developing, the offsets from our drawbells and our undercut, and our development shape that we want to maintain, that it's possible to then schedule draw point initiation timing and sequence, and that can then be reloaded back into PCBC. With those changes in mind, it's also important to look at the mine design. And for us, we had recent ventilation work that decided that actually we should have a little bit of a rethink about how we wanted to approach this mine. And applying that in with a new vent shaft concept, we then completed a redesign. And so the picture here is showing you that the footprint is developed around that pink drive and then across the green extraction level access, and then down the out perimeter drive from the dark blue line there. So that's crucial to make sure that we can operate on primary ventilation as often as possible and maintain efficient development rates, which is good for us and good for the company. We then want to prioritise the central extraction drives to ensure that that cave initiation can start as soon as efficiently as possible. Again, here's a good point for a circle back. So this is when we take where we've got our drawbell starting and whether there's any lead lags that have been introduced by this new resourced and constrained schedule. And this is the bit where I'm more excited about it, is the application. So I guess as a mining engineer, I enjoy the scheduling the most. And we go, well, great, now we have a production schedule, and we have a development schedule, and I have to just use Excel. Trying to get away from that. So what did we do? Decided that PCBC's had a whole lot of great work put into it. It's mixed all the grades, and if I put in that in just as a direct block model, I'm going to mix the grades again and throw away all the work the team's done, and they're going to be quite angry. So instead, we've directly exported each month of production as a single block into a new planning block model, we're calling it. And I've made a corresponding slice within the cave shape. So you can see all of those red shapes equal 1 month. And for a block cave, you're going to have a lot of them. So we thought that was quite good. We've put that all into, for one cave, why not do it for all of them? And so on the left, you can see E22, that's our current project. You can see the cullet drives, they represent a development schedule straight out of Deswick, which has been resourced and constrained. We have the green E48, that's our existing cave. We have our new cave in the blue, which is E26 Lift 1 North. And then those lighter colours below it would be the 5th and 6th level SLC, including development drives. We're quite fortunate that we also have some open pit projects. And because it's in Deswick, we can schedule those as well. So all of these resources have been constrained with lead lags, appropriate resourcing, and hopefully can create a somewhat accurate schedule. If you can assume some artistic license for those that know how cave mounds are generally developed, this is a very short video showing approximately 20 years of mine life in about 30 seconds. Each one of those slices represent 1 month. So for simple people like me, it helps me communicate what I intend to plan to do, and makes it very easy to tell my managers that this is how I want to mine. So in conclusion, scheduling the block cave remains complex, and there are several stages of data reconciliation, modelling, design and scheduling that you have to complete, and I don't know a way to stop that. But conducting this process over and over again for E22, we've identified that if we integrate production data in the development schedule, we stop that mismatch and that uncertainty of are we even initiating the cave in the right spot, and how can we be sure that we've added in the production plan in the right spot. We found further benefit by addressing the cave's establishment point and drawbell sequencing along with our development rate, that we've been able to match those drawbell blasted tonnes and undercut blasted tonnes with those in the initial PCBC schedule. And how did we go with that? North Parks have been using that for our production plan this year. Seems to be working pretty well so far. And that's all I have. Thank you.
All right, we're doing well for time, so we do have some time for some questions. We've got one that's over here.
Thanks for the presentation. Just a question on the first part of the presentation about the linking between the development and the production schedule in PCBC. There is a tool for PCBC and which is actually under PCSLC for undercut and development. have you given it given it a try to use that one? Because that the main purpose of that tool is to create the link between development and the production schedule, and it actually works very well.
Yeah, we haven't used it in this application. Or I guess I can kind of say we have looked at different drawbell designs and undercut designs and the integration of those two. And doing it this way allows you to check both options. But no, if there's a tool off the shelf, that would be great to use as well.
Yeah, I work for the Dassault system, Jovia. I would be more than happy to talk about that app.
Yeah, no,
Thanks.
happy to catch up with you.
Another question? Yep.
Hi, Claire Sherbier from Oz Minerals. So I'm familiar with PCBC and the joys of scheduling in the program, and also with PGCA for our SLC. The question that I had with the iterative process that you have, given it's going from sort of the planning program to the sort of operational of what the draw call is, how do you sort of make sure that when you're issuing that draw call and you've sort of brought in the reconciled information and then your models being updated with that new grade information, that with the new draw call that you send out, you're not potentially overdrawing or underdrawing by setting new targets? So how do you make sure that when you sort of update your models that you're not potentially overwriting stuff that you've already got in the plan being executed now?
I guess that's a good question as well. At this stage, we're using it at a less granular detail. It's for annual production planning purposes. We would like to implement it out at greater detail. But part of the auditability I spoke about was that you keep track of your block model throughout the process. And because it's quite visual, even if you don't want to open the schedule, you can interrogate what's there and verify what's been put in. So there's always those steps. If you were to go solely through PCBC and you've run scripts, it can be almost impossible, at least for us, to find what assumptions were used in where. At least you've got some form of trail doing it this way.
Yep, another question down the front here.
When you were showing the layout, I've seen there are many half drop point. Why you are not developing the entire drop point? According to the Chilean experience, when you have the half drop point, the productivity is not so good. It's not comparable with the entire drop point. It's less efficient.
Yeah, absolutely. And I'm probably not the best person to speak about that question. But yes, they are getting toward the marginal areas of the cave. They're just for ramp up purposes mostly.
But usually it's more convenient to, even if you have a lower grade, it's more efficient to construct the entire drop point to have a better productivity.
And that's good feedback. Yep. Thank you.
Do you have time for one more question? Question. I guess I've got a question is around, I guess a really interesting point you made, Chris, was we use these really complex, sophisticated tools and then we just put everything back in Excel. Do you think that's something we'll ever get away from?
Well, this process hasn't managed to do that yet. I'm hopeful that one day there will be a turnkey solution that's able to do caving, and the wider caving community will accept the outputs from that and then also schedule as well. Until then, I don't know.
Very good. We do have time for one more question if there is anything. Scott down the front here.
Thanks, Chris. Really interesting presentation, especially the use of Deswick for the slices of the cave progressing. I did notice that they were all quite flat. So does that mean you're assuming a flat progression of the cave, or is it more just reflective of the tons by period, not necessarily of the actual cave shape you're going to get as that progresses?
It's a quite literal direct interrogation, so that it's only there for the purposes of animation and to bring into the schedule. So PCBC's done all that hard work mixing it properly, and the last thing we want to do is then change it. So we want it to be exactly as it was provided to the scheduler to put in.
How big's your Deswick file, by the way?
Without surfaces, it's about 30 megabytes. So that's including all sites. I didn't touch on it, but because I'm not just trying to sell Deswick to everyone. We then put it into the blend package, and it's just the stockpile inventory management surface add-on essentially.
Thanks.
Excellent. Thanks for a very great presentation.
Okay, thank you.
Thank you, Chris. Our next speaker is Dr. Stefan Arndt, and today he's going to be presenting investigating an economic and risk metrics using design of experiments in a fully coupled caving geomechanics simulation. Welcome, Stefan.
Thanks, Alex. So as you can see, I tried to squeeze the whole paper into the title. This is work we've done with my colleagues Daniel Villa and Firouz Kurayari from Dassault Systems, and also want to acknowledge the collaboration with Barry and Lover from Rio Tinto. So 4 years on from caving 2018 in Vancouver, we presented a paper on the coupling technology that we developed back then. That's work that started in 2016. Not exactly new. The industry has been playing with coupled solutions for about 10, 12 years now. The key was we had cellular automata in GEMS PCBC as a CA3D module. And we also have the technology for geomechanics simulation, Abacus, in the Simulia brand in Dassault Systems. So it was an obvious idea to put those together and come up with a fully coupled, fully automated workflow that you can drive directly from PCBC. Back then, first concern was, does it actually work? So we had some benchmark cases that we looked at the actual propagation, the coupling mechanism itself, overhanging fault, overhanging domain, second panel, second lift, and scenarios around delayed entry, hydraulic fracturing, and these things. And what we call the Pac-Man graphics there, we can still produce those in terms of what is happening in the CA3 model. We had some interesting observations like the fracture banding, the paper that Dan Podwin Cummings was presenting on the new conceptual model for caving. We actually saw that in our models. I think part of the reason was a very fine mesh, like 5-meter cells in those test models, and a regular mesh, which was able to actually allow those bands to form, mainly based on a nonlinear finite element analysis using strain softening material. It's a basic more Coulomb. There's some internal stuff that's in the paper about fitting that to a Herc-Brown envelope, depending on the depths. But this was a starting point for us where we were 4 years ago. And from there, we really wanted to look at the next steps in terms of automation and using this tool repeatedly to investigate the risks and get a deeper understanding of the caving project. Now, this slide here, I felt like it's not really necessary to put that up because we probably have like a combined 1,000 years of industry experience in the room, but it's a mistake I made before because we have young talent, we have students that come to the conferences, and it's actually useful to spell it out sometimes. The pictures, 2019, we had the International Conference on Mining Geomechanical Risk from the ACG, and Carmen Flores was contributing a fantastic keynote there, and he'd done the industry a real service in providing the illustrations in that paper as well, which are absolutely fabulous. Geomechanics drives the ground support design, the life of mine performance. We look at stress strain changes, seismicity, activating faults, but also the shape of the cave has a lot of impact on the material we're actually getting. I think yesterday's workshop, Sarah was very clear about how important it is, the constraints that you have from the cave when you use PCBC. So the assumption everything is vertical is not really true, and we've seen that. And also, what is the size of the air gap is an important question, like reduce the risks there of an air blast. And subsidence breaks through the timing of that. We mentioned the famous paper from Jeff Capes yesterday, Truth is Stranger Than Fiction, about the story of Newcrest back then. So we really want to understand what's happening as early as possible in the project here. And one comment yesterday from Alex was when he goes out and first thing is he collects all the data, he puts it back together in 3D and shows it. And the feedback he said he would have is, oh, where did you find all the data? So I think we need to push the industry towards the tools. And I mean, that's what we're doing. I'm a bit biased there, but what we see in aerospace, automotive, these tools exist for like 20 years now, and we're not really using them for visualization. So virtual reality, we did a demo with the data set we had, and people that are mining engineers that have like 20, 30 years experience, they take the goggles off and say, wow, this is amazing. You have a different perception than just like an Excel sheet with your hazard matrix and your low, medium, red, green, yellow, orange cells or red cells in there. So this technology is really interesting because once we have these models, we can actually start asking the right questions there. When we talk about automation, the key here is we want to be able to do things by itself. We don't want to spend time in Excel. We don't want to spend time copying and pasting data and managing files. And there is a key element there. Once something is automated, you can do it once, you can do it 100 times. So like Mickey here getting 100 brooms to help him. If you're too young to get the reference, it's a 1940s movie from Disney, Fantasia. It has this beautiful animation in there. So we want to have this workflow automation, and we're using, Daniel Villa was describing some of these technologies this morning for his frequent flyer and trade-off studies there. We have a main component that is our tasks. That can be a design of experiments where we change certain parameters. It can be a Monte Carlo. It can be an optimization module. But there's a key main component that drives this. And everything in that loop from that component that follows has to be fully automated. So there is no direct intervention once you start the process. So we have some tools there around file management. Like if you have a model that's 10 gigabytes that you run on 24 CPUs or 64 CPUs, we're actually doing that. You don't want to waste those CPUs sitting around waiting 5 minutes to copy that file onto external storage. So you put those processes in the background to be efficient there. So there's some housekeeping around there, but the key of that workflow is we prepare all the inputs, and that can be, we're working with text files, Excel files, configurations, whatnot, and that's all linked and tracked to a module that has all the key parameters in there. And then we run the coupled analysis. So for a large model, that can be 24 hours on 64 CPUs. PCBC and Abacus completely coupled to do all the PCBC work with CA3D. So we get the grades, the production, the financial analysis out of that. We get a stress strain model for the whole sequence of the mine there. And that can be like tens and hundreds of months really for the sequence that we're analyzing. And we have the downstream processing side of this. So some examples there, we can look at calibration of an existing operation with the model, or the model with the existing operation really. So look at beacon data, movement, entry to the cave. Analyzing the cave shape is an interesting challenge. I'll get to that on the next slide. Looking at cave height and air gap development over time. And look at grades in a really detailed draw point by draw point, month by month analysis. And that can be important for your financial planning. It can be important for design consideration. It can be important to calibrate a model against operations. And you get new data in, you want to like basically keep calibrating the model every week or every month, really in that context. Interesting surprise for us when we did this was a cave shape is actually difficult to quantify. We've seen enough examples. I didn't want to bring like another Point Acadia on or the other ones on the slides from Masmin or this series of conference proceedings. But what it felt intuitively like, we just look at the distance of the shapes. When you look at them, you probably come up with this is similar, this is not similar. We found it's actually bloody difficult to come up with a useful method. Like the first attempts that we had there were actually coming up with nonsense numbers. So a colleague of mine, Steve Weller, he came up with these ideas, looked at image processing and other work done, and he found that the regularization in a grid of the two shapes, and then the distance transform that we have on the screen here, like counting the blocks that are inside and outside and how far they are, all this obviously in 3D for the cave shape, like millions of blocks, no problem, that is really quick, actually gives you a good quantification of the similarity of a cave shape. I think we're fixing a problem here that we don't actually have yet, but I find if there's one takeaway that might help the caving community in the next 10 years, it's ideas like these, because we need to get away from manually interpreting, like the slowing down the understanding of simulation and analysis in that space. So for me, this was really insightful and actually became quite useful because, as I said, everything in that process loop needs to be fully automated. Like if you start looking at different cave shapes and you have 100 of them, you easily get lost there. Similar with the grades data, production data, just an example here. Usually I would go to little scripting tools, write some Python code for that. And I realized it was actually stupid because these days there's lots of data science tools, there's free tools, we have our own. You can actually do this with graphical interfaces and drag and drop today's world. You don't even need to learn Python code anymore. And this is just about preparing the data to be analyzed. So with the grades that we get out of PCBC, we have that result for every dot point, for every cycle, like every month or quarterly interval, depending on how we set up the simulation. And we want to come up with useful analysis in terms of what is the financial outcome, and not just static, like we can actually analyze the uncertainty around that, like NPV based on discount rate, other assumptions, penalties for the different minerals you might find in the ore bodies that are not desirable. All this can be done in a kind of data science fashion way, and again, fully automated here. So this is just some examples for the automation of the workflow. Now we want to go to the application, and we're both interested in the risks in terms of economics and the geomechanics implication. So again, we have PCBs and Abacus coupled, so we can actually simultaneously answer those questions there. Daniel this morning showed this fictitious data set that we have. We call it the Riga project. It's like a copper porphyry, typical ore body. Really helpful. Like we've done some interesting projects, and sadly I cannot show any of them or mention them. But this one does the trick, and we also use it as a training model because this can be run on a notebook and takes like 20 minutes to run for a coupled caving simulation there. And I didn't actually compare the coupled model that is constrained by the cave shape that comes from Abacus in that coupling process with the vertical assumption that is much further away. I found that is actually not meaningful because we know that the vertical assumption that all the material is available, and as a consequence of that, no air gap will ever form, is actually not true. So what we did here, we used those design of experiments tool to vary cohesion and friction angle. Two simple parameters for our Mohr Coulomb that defines rock strength in a simple range of 0 to 10%. And I just picked the best and worst case out of some 10 simulations there. And I was really surprised to see that we already get 5% difference in NPV within the first 4 years. The effects that you see there in detail, there's some air gap forming. The cave shape is slightly different in the early years. And if you look on the left side, you see that the ore body is highly variable. Highly variable ore body means there's a lot of optimization potential. There's a lot of opportunity to find the right answers there. Interestingly, the cave shapes halfway through and at the end look very similar. Like visually, you wouldn't guess that there is a difference in NPV to expect in there. But what happens there is through the rilling mechanism, in one scenario, you just get some low grade being produced very early on. You catch up later on. And overall, the volume of the cave at the end is pretty much the same. So very different outcomes in a very simple scenario. Imagine how much potential there is in a real life project then. And the other aspect I was curious about was the geomechanics hazards and simply speaking about cave propagation and the rate combined with the emergence of an air gap. So we did a design of experiments here with just 12 different scenarios. Design of experiments is a tool that systematically changes parameters in a way, like one of the patterns is called a Latin hypercube there. It allows us to try those 12 scenarios and find the best one out of those. At the same time, it allows us to get the sensitivity of these input parameters to the outcomes there. So what you see here is we can have a variety of different scenarios. Some have no air gap emerging, some progress fast, some progress slow, and some have a fairly huge air gap. And just early case, and refers to the moment where we had the early difference NPV. We have two different scenarios on the cave basically establishing itself early on. And if you can't read the numbers here, it's all in the paper on the sensitivity matrix. What we didn't do was change the stress gradient. We didn't change the stress direction. We didn't change the mixing parameters in PCBC, and we didn't change the fines migration. All of these you should actually have a look at because all of these influence the outcomes there. So with that, just quickly through some conclusions. Important part is we want a true workflow automation. So we can run it 100 times, we can run it on different computers efficiently, and we can actually work with the sensitivity towards uncertainty. And we talked about these definitions, aleatoric uncertainty, it's the randomness in the world. Epistemic uncertainty is where we just don't know what's there, or we don't know it well enough yet. And using those sensitivities to identify which are the driving parameters, and that helps us to find which is the best outcome that we're looking for, or which is the most robust outcome with the lowest risk. And applications that we've done, different draw point opening strategies, like a chevron front compared to a north-south, east-west, whatever you want. Orientation towards critical faults is one topic there. Uncertainty in rock mass strengths, what I just showed there. And obviously stress magnitude, stress orientation. We had yesterday the comment that we should have hundreds of stress measurements, not just 5. And with that, we want to close the loop between financial planning and geotechnical analysis. So get those silos to work together early in the design process to come up with better scenarios. Future steps, we just saw some comments about Excel and all that. We want more processing automated. And what we're doing here with Dassault Systems, we're using a 3D Experience platform. This is a very powerful solution to have a single source of truth. And also in the future, we actually have opportunities to play with parametric mine design, which is the idea that we can design a whole underground operation based on rules. And if you have to change the design, you can do that. Questions?
Thanks, Stefan.
Okay.
We do have time for one question. Question from the floor? No, I guess I got a question, Stefan, is I guess what do you see as the next step? You know, we're advancing these tools. We've got coupling that's been advanced over, say, a 12-year period. What do you think is next?
I really think getting rid of Excel would be a good step. Like,
Yeah.
true collaboration. And looking at things in 3D, as you mentioned, yeah.
Sure.
That's it.
Any questions from the floor? No? Please thank Stefan.
Thank you. Okay.
Okay, the next paper we held, the next presentation we have is titled A Simulation Comparison of Operating Strategies for Electrified Block Caving Mines. We have two presenters. We have Scott Marager from Oz Minerals, who's going to start the presentation, and we also have Colin Eustance from Polymathian. Thank you.
Is that working? Is that good? Everyone hear me at the back? Cool. Firstly, thank you, Alex, for chairing this session. Thank you, SRK, for sponsoring the session, and thank you, ACG, for putting our presentation on relatively early on in the conference while people are still sort of awake and attentive. Appreciate that. Yeah, so I'm here. I'm a long-term planning engineer at Oz Minerals, working on the Carrapateena expansion and growth team. So I'm here today to present a simulation comparison of operating strategies for electrified block cave mines. So it's a very generic title, but the focus of this paper is on the Carrapateena block caving operations. But the idea is that this process could then be repeatable for other operations heading in towards execution. I'll put that disclaimer up. Rod and Chin have already done a good job of showing that and also covering off a few of my initial slides. So I'll go through them quite quickly because they're very generic introductions to Carrapateena and context setting. But yeah, so I'll repeat again that the Cookita people are the traditional owners of the land we operate on. So we've got a really good relationship with them. You can see there where our mine's located, and Adelaide down the bottom where we are now. You've seen this layout from Rod and Chin's presentation. So obviously the focus being on block caving side of things for this presentation. You can see there the layout of the conveyor declines heading up to the surface. So underground crusher down at the footprint, onto a conveyor, with the ore bodies of the SLC and the BC basically on top of each other. A look at the footprint. So split into two sections. So this paper is purely focusing on the BC1 side of things and the optimization of that footprint. You can see there we've got an off footprint tipple to the top of the page. We've got two accesses. Obviously the conveyor decline coming to meet up with that underground crusher, and the main access decline to access the extraction level undercut. 4 tipples at the crusher. So that's an important part to note with how we've run the simulations. And probably the most important part is that highlight in red. The base case design was done off a 21-ton diesel loader fleet, operating conventionally from draw points to tipples. The reason that's important is, I guess, this next slide details earlier this year that Oz Minerals announced our decarbonisation roadmap. As Craig mentioned earlier this morning, net zero and carbon emissions is becoming more and more prevalent and driving a lot more decisions in mining. So we're trying to get on the front foot, obviously, to map out a path to get to net zero by 2030. As part of that, we're looking at reducing our scope 1 emissions by 50% by 2027 relative to FY21 baseline. Scope 1 emissions referring primarily to combustion of various fuels from equipment on site. Obviously, a big part of that is underground loader and materials handling fleet. So with that previous assumption for the base case of 21-ton diesel loaders, we identified that it was a requirement for us to look at options to excavate the footprint using battery electric vehicles, whether that be a combination of loaders to tipples or loaders and trucks. So that's, I guess, the key driver to why this work package is being undertaken. So I'll just quickly run through the initial methodology. So obviously that decarbonisation roadmap's triggered all these steps, which I'm about to run through now. So firstly, assessing our current base case design and just understanding, hey, can we actually get the required throughput using a battery electric loader fleet? Because if that's the case, then we're happy days. Unfortunately, that had identified a challenge in achieving the throughput that we wanted from using a battery electric fleet with our base case mine design. So that triggered step 2, which was looking at some alternative concept footprint designs. So that's kind of throwing everything on the table, looking at, trucking loops, loader truck combinations, ore passes, that kind of thing. For each of those alternate concept footprint designs, we did a SWOT analysis just to compare each design, identify what's going to be practical to take through for further assessment. Some of those key aspects that we wanted to consider when doing this assessment were, I guess, crusher station tipple location. So is the crusher on the right side of the ore body? Can we move it to a different side? Can we change the orientation of our extraction drives? Is that going to give us a better result by using battery electric equipment? The number of meters obviously is important with the time it's going to take to ramp up the cave. But geotech considerations was probably one of the biggest ones. So we wanted to ensure that we identified and understood the structures, the principal stress directions, and the orientation of our drives and our cave fronts relative to that. And obviously ventilation considerations is always a big part of it, given the depth that we'll be mining at for the block cave. So the SWOT analysis reduced those large number of concept level designs down to about 3 options, and we progressed those 3 options into a more executionable analysis to test for practicality to actually be able to execute the design. So I guess some of those key points that we wanted to make sure and look at is what's a day on the level look like? What are the vehicle interactions going to look like? For a loader to get to the workshop, to get to the tipples, for ancillary equipment to get in and out, or the traffic flow is one of the bigger considerations with the limited number of extraction drives that we have on the footprint, and any ventilation impacts. So those designs were then provided across to Polymathian, and so Colin's going to run through the assessment there, along with some key input assumptions for the model. So we used a lot of OEM data for vehicle performance assumptions to feed into the model. So I guess some of the things like the bucket size and bucket factor, the speeds of the loaders, acceleration, deceleration, and tipping times and bucket times, bucket fill times were probably some of the key inputs that we needed to understand. And there's a few other things there. We had some driver availability assumptions around, when do we do hang-ups, secondary breakage, how many extraction drives do we estimate are going to actually be online at any one time. I want to hand over to Colin to discuss the simulation. No, don't think so.
Do you need to switch it? Oh, there we go. Excellent. So what I'll do this afternoon is take you through a quick run through the simulation model and keep it at a fairly high level so we can move on to talking about the different operating strategies that we've tested and understand the pros and cons of the different operating methodologies and their relative performance. So the focus of this analysis is on production level performance. So you can conceptualize the model that we use as three separate areas, I suppose. There's in the middle, mostly in yellow, we've got a detailed representation of the production level network and all of the equipment operating on the network, the acceleration, deceleration, interaction, movement, maneuvers to pass vehicles. Upstream, we have a representation of the PCBC inputs, the caving profile, and therefore the draw call for the different draw points, a representation of hang-up frequency associated with a particular point in the life of the mine and oversize events, a representation of the drive closures and availability required for secondary brake to service those draw points, and therefore unavailability for those draw points for production.
Downstream, we have a representation of the materials handling interface that the loaders or trucks are tipping into, and the important part of that representation is the rate and unplanned outages due to tramp, and a representation of the coarse ore bin control system, which ultimately results in red lights that might delay movements on the production level. So the main driver for the model, we're looking at a particular point in time. Once the cave's ramped up to full production, but you have a relatively high or higher rate of hang-ups and oversize events earlier on in the life of mine. So those inputs drive the draw call, which is translated into movements for the loaders. We're using a ratio bogging methodology, which is similar to the methodology used in many block caving operations, which are attempts to keep the number of tonnes drawn from each draw point to within a tolerance associated with the desired caving profile. The same thing again, and just to explain this representation that you'll see a few times in different formats as we look at different operating methodologies. We've got red draw points there which are hung up or oversized, so they're not available for bogging at this point in time. We've got the green draw points are open and available for bogging. The magenta ones on the right-hand drive there are outside the tolerance, and the reason for that in this particular scenario is because there's a reduced number of draw points, so they've been bogged to the extent that the caving profile will allow at this point in time. Right, so I'll move on to a comparison of the different operating strategies. So what I'm going to do is just step through each of the operating strategies that we analysed and talk about how each of those strategies operate and how they perform relative to each other, and we'll have a look at some summary results after this. So everybody should be relatively familiar with this style of operating a block cave. This is the typical the draw point to tipple shuttle operation that most block caves operate with. The advantage of this style of operation is it minimises the distance from the draw point to the tipple, so it's fairly efficient at low throughputs on a per loader basis. The problem with this style of operation, particularly as you're trying to ramp up tonnes or you're trying to achieve high throughputs, is it's ultimately limited by the number of loaders that you can fit on the footprint. So in this example, we've got a 9 extension drive footprint. We've got 2 extension drives out for road panel closures and secondary brake, which leaves us with 7. So this was the default footprint that we were looking at. It achieved through the required throughput with 21-tonne diesel loaders, but the use of 9 extraction drives was non-preferred because it takes away from the later stage BC2 operations. If we go down to 18-tonne electric loaders, we're falling short of the throughput, and particularly if we go down to 18-tonne loaders with only 8 drives, 6 operating drives, 6 loaders, we're well short of the throughput target. So what do we do about that? Using the same sort of operating methodology, there we go. Look at that. Okay, so this is the same footprint operating with as many loaders as we can sensibly operate on this footprint. So there's to increase the number of loaders beyond 6 for the available drives, or 7 in this case, we've added a second LHD in each drive, and they're passing at the turning bays close to the tipple there. The problem with doing that is that most of the time for the second loader is just spent waiting for the other loader to pass. So the improvements for using the same operating strategy and just trying to force more loaders onto the footprint, it doesn't get you the throughput you need. It just adds to the delays on a per loader basis. So this is the reference operating strategy we were looking at for 18-ton loaders, and falling short of the target that we were looking for to achieve. So you saw in this, the previous slide that we're losing all of the benefits from introducing more loaders to delays in the turning bays. So what we've done here as an alternative operating strategy is introduce single directional loops. So rather than fire the last draw point in the last drawbell, in the drive, you can say that you're using that to form a loop operation. The advantage of this is that you can continue to add loaders to operate on the footprint without excessive delays. So you can see this operating. So the advantage of this, there's a longer tramming time, but you can continue to add loaders to the footprint and reach a much higher target. The other thing you can do with a loop operating strategy is seamlessly move from a typical draw point to tipple shuttle to a loop operation for the whole footprint by successively introducing loops. So you you retain the efficiency of the default operation by and then add the extra capacity that you get from being able to add more loaders into the paired drive operation to bog the southern draw points. We also looked at trucking operations, and the advantage of this sort of operation is you can use a trucking operation to move the tons from the southern draw points to the tipple, and therefore shorten up the tramming time for the loaders operating in the drive. The disadvantage is that you add significant numbers of equipment fleet to be able to do that. A similar operation here we're also using a trucking operation in the north. Disadvantage of doing that is that you only gain marginal improvements in the north and add significant numbers of trucks to do it. Here's an example of the trucking operation. This chart shows a relative performance for the different operating strategies. So you can see the x-axis there as this is the number of equipment, or the size of the equipment fleet required to achieve a certain throughput, and the throughput on the y-axis. The red line there you can see is the reference operating strategy that most block caves operate at, and here it's up to about 6 operators loading. It is fairly efficient in the drive. When you start to have to introduce a second loader into each drive, the efficiency reduces, and it barely reaches the target, even if you try and saturate the footprint. The yellow line is using a drive loop. So it's less efficient initially, but it continues to be able to get more tons because you don't get those interactions in the drives. The blue is a hybrid between the two, so it retains the efficiency of the shuttle operation, but then trends towards the option 2. The trucking loop scenarios, that just having a few trucks in the south is fairly efficient. The north is fairly inefficient because of the additional trucks required. We did a bit of sensitivity analysis to understand the ratio between trucks and loaders, and that was interesting in that the most efficient operation was less trucks than the number of loaders. Another interesting artifact of using the drive loop operations is the presentation at the tipple is much more regular. So instead of getting variable throughput or variable tipping, it's much more consistent, which is much easier to manage for the materials handling system at higher throughput and need smaller bins. So I'll just hand it over quickly to Scott to conclude.
I'll be very quick. So conclusions from this work is that there are additional alternate strategies that were capable of reaching the target throughput, given the assumptions that we put in the model, with those loop and the hybrid options, the one shown here on the right being those that are most efficient. There's obviously some further work to be done to refine a few inputs and test some sensitivities, but yeah, that was the main conclusions we got from the work. So yeah, thank you very much. Thank you, Colin, Kevin and Celine from Polymath for being involved, and thank you for the internal review from Oz and from ACG. Thank you.
Okay, and we are at the limit of time for that presentation, so please thank Scott and Colin. Excellent presentation. Any questions for Scott and Colin, please see them in one of the breaks. Thank you. Okay, our next presenter this afternoon is William Bennett from Mining Plus, and his presentation is entitled Assessing the Reasonable Prospects for Eventual Economic Extraction of a Caving Project. Welcome, William.
Thank you. Well, good afternoon, everybody. I'm going to be talking about assessing the reasonable prospects for eventual economic extraction for a caving project. Now, I wrote this paper after a colleague of mine, Andrew Fowler, prepared an MRE or mineral resource estimate for SolGold's Alpala project. Andrew is a geologist and I'm a mine planner, so he'll probably give you a better explanation of what the reasonable prospects are and why they're important. But my understanding is that what differentiates a geological deposit that's known, that has a certain level of confidence, from being a mineral resource is, well, one of the facts at least, is there has to be reasonable prospects that you might one day mine it, or might one day be able to mine it. For example, a few years ago, I was having a chat with a friend in a pub, and I think he was saying to me, "Oh, why'd you bother mining gold? There's gold in the seawater." And I didn't think too much about it until recently, when I did a little bit of Google exploration and found out that he was right. And there are apparently $800 trillion worth of gold in seawater. But that gold exists at grades of micrograms per ton instead of grams per ton, and as such, you couldn't really economically extract it. Hence, that gold in the seawater, it may well exist. It may be a reality exists, but it can't be reported as a resource. Now, these criteria for reasonable prospects for eventual economic extraction has long been a factor for reporting a resource. But what has been changing in recent times is there's been a sort of a trend for increased rigor in how that's defined. Started off in the open pit world, where I think they're probably, I hate to say, a little bit ahead of us in terms of the way they do things with algorithms and such. But it's starting to make its way into the underground space. One of the ways this rigor comes in is to define a constraining volume for the resource model. So for the resource model. So what that is a 3D representation that goes around the outside of the block model and delineates the portions that have the right sort of geometry to be mined from those that never can. And essentially, That constraining volume is hopefully excluding material that will be too deep to mine by some sort of open pit method, too low grade or discontinuous to mine by an underground selective stoping method, or of insufficient quantity or appropriate geometry to be mined by the caving method. Now, it's a fine sort of blurry distinction between what are the reasonable prospects for eventual economic extraction and what a mining study would be. Often, though, that resource report gets made before the mining study is being completed and before you've really got a mining strategy. So it's important to differentiate them. And it needs to take into account things that the geologist should reasonably know, so the grade, the geometry of the deposit, once they've done the modelling, but it shouldn't include things like the mining strategy. So in coming up with this criteria for a deep deposit that was going to be mined by caving, the obvious thing to do seemed to be to look at what was being done in the near surface deposits in the pit and try and copy as much of that process as was applicable. It's relatively straightforward to use pit optimization software such as Whittle to define a pit shell which has sort of the maximum economic limit to be able to mine. Use long-term metal prices, a revenue factor 1 for the pit shell, and sort of standard mining costs and wall angles. And that might yield the mouse pointer there. That might yield a shape somewhat like the black one shown there. It's important to note that within that black shape, that's the maximum economic limit, there may well be some, there hopefully will be at some point, a mining plan. And now those mining plans, those sit within that maximum economic limit. And then they'll change around depending on the mining strategy. So one mining strategy might be to mine a small starter pit to get early production. And then later on to move to a final mining pit, which is selected to maximize the NPV or IRR or one of those metrics. The important bit is if those pit shells can sit within that economic limit, then regardless of where they are, that economic limit will stay in the same place. The economic limit won't change as a result of the mining strategy, and hence it's really useful. It's relatively straightforward to use that economic limit to be the constraining volume and say everything within this has reasonable prospects for eventual economic extraction. Everything outside of that, it seems unlikely that you'll ever be able to mine it. Moving deeper, once we get to the high-grade deep deposits, it's away from caving and it's less mature, but you're sort of starting to see this sort of increased rigor in stoping mines for reporting the RPEEE. There is an algorithm or a few algorithms for reporting stopes, mineable stope optimizer, and these essentially put a minimum mining width, maybe a minimum dip criteria around the deposit, and segregate it up into a whole series of mining blocks. A little bit different from the open pit mine because those mining blocks can be mined out top down or bottom up. It's a much more flexibility. But what doesn't change is the size of that economic envelope. So if there's low grade marginal stopes on the outside of those stopes will stay break even and marginal, regardless of what you do with the high grade stopes. So they're relatively independent. So to contrast the stoping case with the open pit case, we've got a situation where we've got an algorithm for both, which is really good because obviously takes a little bit of work away from the mining engineer or the mine planner. And more importantly, it's a repeatable, transparent process. If someone comes to audit it, you just need to recite the parameters under which that was created, and hopefully the auditor can go away and replicate those results. That takes us to low-grade deep deposits that might be mined by caving method. Again, we do have caving optimization software. Footprint finders are probably the most appropriate here. And those footprint finders can generate an economic envelope. The problem is, to do that, you need to select a footprint. The selection of that footprint is generally based on a mining strategy. If the mining strategy changes and you get a different footprint location, then the economic limit will change. It will be appropriate for that particular footprint, which obviously is not so great for the constraining volume because we're in a situation now where our constraining volume for a geology model now depends on the mining strategies. Often we haven't come up with the mining strategy at this point, so it's a little bit tricky. I've drawn up a couple of examples of how that might be the case. So the one on the right is a sort of maximum extraction case for this deposit where we've got a low grade ore body with a high grade pod at depth. So in the complete extraction case, we've split it in two lifts. There's a low grade lift at the top and then a higher grade lift below. This achieves complete extraction of the resource, which is obviously good under some mining strategies, but under an MPV sort of strategy, it's not going to be so good. That high grade is going to be delayed to the end of the project, and then that's obviously going to be not great for project value. A more likely mining strategy is the one we see on the left, where the first footprint is placed so that high grade gets extracted straight away. The low grade gets extracted later. We maybe lose a little bit of recovery at the top of the deposit where we've sort of exceeded what we believe is the maximum height of draw. And at the bottom of the deposit as well, we've lost some material. They're both legitimate mining strategies. The point I'm trying to make here is that depending on the mining strategy, that economic limit changes, and hence it's difficult well, relative to the pit or stoping case, it's more difficult to develop an RP/EEE constraining surface. But another example here, this time we've got a high-grade core surrounded by a low-grade halo. If the production rate is high, we can probably mine everything at once with a single footprint. The height of draw progresses through the cave. We mine the low grade with the high grade, but the mill's big enough to handle it all, so it's a good mining strategy. If, on the other hand, we've got a constrained production rate, maybe there wasn't enough money to build a big mill, then we might want to bring that footprint in and concentrate just on the high-grade core. Again, it's a legitimate mining strategy to maximise the MPV for the conditions, but the problem is we've lost that sliver of low-grade material or lower-grade material at the edge of the footprint. We're able to recover it at the top of the footprint, but the portion at the sides is now probably too narrow to cave. So again, we've got a legitimate mining strategy, but that's changed what our economic limit would be. So faced with these problems in how to use optimization software to determine that RP/EEE surface, my colleague and I came up with three potential approaches. In the first approach, we used footprint finding software, and these are potential approaches. So we did some of them and not all of them, but this is the plan. We used footprint finding software to go through the deposit, test all the potential footprint locations, and then selected the one, not the one that gave us the best NPV or IRR, but the footprint that gave the best recovery of the deposit. As you can see, it's not superb. There's some material left down the bottom, some material left up the top. Again, I must emphasize these are schematic pictures to illustrate the sort of problems that we're encountering. Given that, I mean, it wouldn't be a very good mining plan because, of course, it's highly diluted. It's not really targeting high grade. It's also not a very good shape from an RP/EEE point of view because we've left a lot of that resource behind, or we've left a lot of that material behind that we really would like to report as a resource. So to try and improve the recovery, we came up with approach 2. Now at approach 2, we used the very same algorithm. We ran those footprints at multiple different levels. But then instead of just selecting one of them, we Booleaned those shapes all together to give the single shape you see on the right. Now the rationale here was that if a block in the deposit fits into the economic limits on one footprint location, and that footprint location is valid, it seems reasonable that that does have good prospects of economic extraction under some form of mining strategy. So the justification is good. Obviously, in terms of the resource recovery, or sorry, the conversion of the deposit into resource, it's also quite good. We've covered most of the deposit, but if this was a mine plan, we would say this is particularly bad. There's a huge amount of dilution on the football, and in the mine planning sense, it would just be a bad plan. In the sense of the work we're doing here, it's probably even worse because what we've done by including that material, we've overcalled the size of the resource. It's quite interesting to note that essentially this is the sort of maximum dilution case. So in each column, that ore will be diluted down to its very lowest value that it can support by that waste material. So even though this is the sort of maximum resource, it's probably not appropriate for the task we're using. With that in mind, we came up with this third approach. Now, in this third approach, we defined a minimum mining unit. That minimum mining unit, maybe about the size of one of the yellow squares, was designed to be about the same size as a minimal block cave. So it had a small height, maybe 200 meters, and a small span, maybe 100 to 150 meters. The sort of thing that you would say, yeah, this is the minimum size under which we could potentially have a block cave. We then tested that minimum mining unit in all the different positions within the block model. So and evaluated what the tons and grade were. We then found the position that had the very best value. Now, with the very best value, it seemed highly reasonable that that would be economically extracted. So we flagged that as part of the constraining volume. And then the key step here was we depleted that material from the block model. And the reason we did that was to stop that high grade then carrying other lower grade areas in the way that we saw in the second approach. We then carry on moving that block round, finding the next best position of value, flagging it, depleting it, moving to the next position, and repeated that process around and again until we'd covered the whole deposit with these yellow squares. And the very next position was sub-economic. That gave us the constraining volume we see on the right. Now, obviously, if we were going to do this process manually, it would take an awful long time. But luckily, the process I've described is actually the same one that DataMine's MRO algorithm uses. So it takes a slope and floats it around successively, finding the best location, flagging, depleting, and moving to the next location. So this third approach sort of met our criteria. We had a method that was automatable using an algorithm, and we could repeat that process based on a smaller number of parameters. And we had a method that gave a constraining volume, which was independent of a particular mining strategy. So again, it filled sort of criteria after and matched well with the approach that's being used in open pit or near surface deposits. We applied this approach to SolGold's Alpala deposit. The Alpala deposit is a large copper, gold, silver deposit. It's located in northern Ecuador, and it's recently completed a PFS study. Now, at the time we were doing this RP triple assessment, it was for a resource update that was being done after a PEA study. So we'd done a mining study, but we were able to use all those parameters we'd used in the mining study. But what we didn't want to do was to just take the footprints that had been defined in that mining study and define an economic limit for them, because that would assume that the mining study in the PEA was the only one that there was. So instead, we used the parameters where we could and used approach 3. You can see on the right, that's the picture of, or sort of oblique section of the geological model, it's shown in grey, and then the constraining volume shown in red. So to do this work, in terms of the parameters we used, as I said before, we tried to copy as much as we could from the open pit method. So things like metal price, metallurgical factors, and offsite costs were identical between a near surface deposit and a deep deposit like this one. So we're able to use that same process. With regards to the minimum mining unit span, in this case, it was relatively straightforward. We'd completed a PEA study, so we're able to use the same parameters that have been defined in that PEA in terms of minimum span and apply it to this project. One interesting thing to note was that the span was actually quite a bit bigger than the one we'd calculated if we used the critical hydraulic radius. I don't think that's atypical for block caves. I think the point of note here is that for RP Triple-Es, it's probably worth benchmarking these parameters rather than going back to first principles. With the minimum mining unit height, it seems unreasonable that you could put a footprint in and then not draw anything. The problem is it's obviously going to be very expensive to do that. We've got the costs of setting up the drawbells and the extraction level. And also there are effects within caving, so vertical mixing being the big one, which typically have a fixed component. So vertical mixing happens below the height of the interaction zone. So we needed to put enough of a minimum mining unit height in so we could cover those fixed costs and fixed effects such as vertical dilution. So made that shape, the minimum mining shape, and floated around and achieved the red shape we could see in the picture. Within that, we reported everything in the in situ model that sat within that red shape. Now, of course, if this was a cave, we would have effects like vertical mixing, recovery at the bottom of draw columns. But the complexity of adding those things into a geological report just seemed too tricky. And we also drew on the fact that there are some mining factors that aren't considered. So unplanned dilution, and that's one of those, vertical mixing causes one of those effects, isn't usually considered in reporting an RP Triple-E for an open pit project. So again, we didn't include it here. Planned dilution, on the other hand, we did include. So you can see there are some spots where the red shape has gone outside of the resource model, and that's places where the resource model was below the minimum mining unit span and the shape has got bigger. Now, block caving is non-selective, we felt that it was important to recover or to report all that material, even if we wouldn't like to mine it. If you did pursue a minimum mining unit in that location, you would have to. So we reported that. And for the sake of clarity, we included that as a separate line item in the resource table. So unclassified must-take material. I think that pretty much ends my presentation. I hope you found it interesting, and I'd like to thank my co-author, Andrew Fowler, and our client, Solgold. Thank you.
We do have time for one question. There are any questions for William?
Okay, hi. I'm not terribly familiar with these, but if this is expected economic extraction, but I also noticed there were some places in there where you were including offsite costs and things like that. To what extent does this include processing costs, things like that, that would turn it, where we would be looking at turning something into a resource instead of just a potentially valuable chunk of rock?
Yeah, so my understanding is that the reasonable prospects for eventual economic extraction needs to include all those effects. So the processing and recovery, the offsite costs, all the things you need to do a mining study, but under somewhat different parameters. So the metal price is the long term, because we're not looking at extracting it under a specific set of conditions, but the mining factors that will apply, the offsite costs, all those things need to be included, albeit at a much higher level, because when this work's being done, there's probably that sort of information available.
Thank you.
Excellent. Thanks very much, William.
Thank you.
Okay, our last speaker for this session is Marley Human. She's from the BBE group, and today her presentation is ventilation requirements of caving mines.
Thank you. Today, I'm Marley Human from BBE. We're going to speak about the ventilation requirements in different cave mines. Today, we're going to start this presentation having the end in mind. So upside down approach, because all of us are engineers, geotechs, you know how your mine looks. So we're going to start at the production phase, working our way down the infrastructure, the services, development phase. Then we're going to check that all the ventilation design criteria are met, and that's what I'm after. And then we're going to circle back to the mine design and making sure that our production phase and development phases are actually covered. So if we have a look here, we're starting with block cave mines today. What is very important here is there are various footprints of how a block cave mine can look. You've got to consider we're going to have a single access drive, you're going to have a central perimeter drive, you're going to have what type of vehicles you're going to be having. Is it battery electric vehicles or is it diesel vehicles? And this is just a typical example of a block cave mine in PNG. Here we've got a different mine in the US, panel cave mine with different interim drives, single perimeter drives with multiple panels that has to be accessed. Here we've got a block cave mine in South Africa that actually is accessed using twin perimeter drives. And here you can see it's very important where your distribution of your air becomes very important between the different extraction drives that you've got. And considering how you're going to ventilate each of those extraction drives become very important. Are you going to design a minimum velocity? Are you going to actually support your mining activities? And how many crews are you planning to have in each of these phases when you actually access the footprints during the development and then the production phases itself? Here is an example of a macro block cave in Canada. Here you can see it becomes very tricky and important to think how you're going to go between your different macro blocks during the transition phase, where if you have this interim perimeter drive, it very quickly becomes tricky where your personnel are going to be, how you can interface with your vehicles, and how you can actually access and ventilate those extraction drives, because you're going to have secondary breakage that you want to actually blast, and how that's going to interface with your production phase is very much impacted during those stages. Here is an example of another panel cave mine in New South Wales, using copper, mainly producing copper. This is a quite large footprint, and you've got to determine very carefully how you're going to interface between these different macro blocks, and where you're going to place your infrastructure, your internal vertical shafts, where your crushers are going to be, but we'll talk about that shortly a little bit more. Here we've got an example. We're going to go over now to sub-level cave footprints. So how you go down your decline, access your actual footprint, how you're going to access each of these extraction drives and production drifts are very different. Mainly we make use of force ventilated systems during these footprints. Here is quite a large, narrow type of footprint where you really have to decide how you're going to access your footprint. Is your mine going to be from the middle phasing out? Is it going to be from the one side to the other? And how you actually replace your development and your ventilation that supports your production sequence is very important during these stages. Then mine design that we've seen frequently today is here we need to decide what this actually shows us. We've got a decline that we use as our access, and where you place your fresh air raises and your return raises during the development phase actually helps you to access your footprint much faster. So how you actually ventilate it, where you place these shafts relative to your decline during the development phase really becomes an important consideration when you want to access a footprint like this. We sometimes see with sub-level caves, the intake raises can be in the center with your returns on the extremities of the footprint, but sometimes it's the other way around, as we can see in one of these older mines. What you also have to decide, sometimes you get your footprints where there's a little bit of a dead zone that you don't want to produce in that sector, and how you're going to where you're going to place your ducting and your fans when you want to access a smaller footprint, as we can see over there. Here we've got another example of a sub-level cave. And here you can see the return airways are actually in the center of the ore body, as opposed to where we typically see it on the outskirts. So with an intake here on the one side. So where you place these internal raises become very important from a ventilation perspective, as I said, during your development phase and your production phases. Here we've got a kimberlite ore body in South Africa. Here we can see multiple intake and returns. Specifically for this mine, you've got to consider, in the previous designs, we've mainly seen wet drilling, whereas here there will be only dry drilling because of the ore body. So now you no longer can consider having intake or force ventilated systems, but you actually go for extraction ventilation type systems. And the whole dynamic and your duct selection and the pressures on your main fans changes because of that. You mainly will see higher pressures in extraction mode. Your ducting becomes very important to select that correct, as you can have actually your closure of your ducts because it's now under negative pressure the whole time, and it's not just forced open by your forced ventilation duct. So all those considerations need to be carefully selected and thought through when you're going through your design and planning phase. Just going to quickly speak about the actual infrastructure. So typically for these mines, you can access your ore body using either shaft systems or a decline system. In this particular case, we can see it's a by shaft system where you have fresh air risers or blank sink shaft there are the various sinking methods of, getting to your shaft, to your actual ore body. In this case, we would typically design the ventilation rises, the intakes between 8 and 12 meters a second, where you can actually go in your return rises. You can then go up to, we've seen places up to 30, even 35 meters a second, which is not economical, obviously. So before you start a trade-off and a design like this, it's very good to trade off your economical velocity, look at the capital cost that it will actually cost you to sink these shafts, look at the cost of your actual fans, and then compare that to the life of mine that you're going to pay in operating cost. Yeah, you can see an example of where you access through a decline. Typically, the declines, if it's an intake velocity, you don't design for higher than 6 meters a second, because most of your people and personnel will walk in there. You will typically have your conveyor in one of these declines. So you don't want dust pickup to ruin or actually expose your people to nasties or any hazardous substances. Here we can see an example of where your shafts are actually clustered together. It's at the intake of the at the shaft. You could also consider having return rises at the extremities of where your pit would typically sit, or just on the outskirts of your pit. Sometimes these return passes even hole into the pit if obviously you're outside the zone of influence where you will lose these shafts over life of mine. You also have to consider and making sure that when you place these holes and possibly the fans that actually extract from these holes in your pit, it could be on the benches, but you've got to make sure that they will actually be maintained over life of mine. All right, then typically what we have to also consider during infrastructure designs is we've got an opportunity, particular with block cave type of mines, to decide, are you going to have your intake ventilation drives on the same level as your extraction level? And you could actually consider having it below the footprint if it makes economically sense. Obviously, it all depends on how many tons you're going to be extracting from your mine, what the ventilation needs are, and then how hot your mine is. Very much frequently we see in the subtropical areas and in our Queensland areas, the temperatures on site start off very warm. So you quickly, when you introduce mechanized equipment, you get to warm temperatures of exceeding 27 and 30, even 30 degrees wet bulb, which is very dangerous to personnel. So you actually have to have mechanical cooling to make sure your personnel are safe. And if you have these intake levels on separate levels, it actually provides an opportunity to place your air coolers, if they're placed underground, on those particular levels. You also have the decision to make how you're going to transport your ore from the footprint. So having separate sacrificial or secondary conveyors on a separate level provides that opportunity. Otherwise, you can also consider having haulage levels where your trucks will go and then tip into a central crushing station, and then your rock is transported to surface either through the shaft system or through a conveyor set. Here we see just a quick example of an SLC mine. What is typical of SLC mines is your internal ore passes. So what is quite novel of this design is there are return passes close to your ore passes, which actually provides the opportunity to have all that dust during the tipping phase into the ore pass that is extracted directly to your return air passes. So it makes it good from a visibility perspective, and it just ensures that all that throwback of the dust is not into your footprint. The next consideration, and very much many times we make use of ventilation modeling, whether you use Vensum or PCNet or VUMA, you can actually decide Well, you make use of those software that informs you during the design phase of what you can expect on your fan pressures. It also gives you an indication of what your refrigeration system design need to be, or whether you should add actually heaters where it's cold mines or cold areas. And you need to make the decision then during the planning phase, whether if it's a surface application, whether it's horizontally faced fans, vertical fans, or whether your fans will actually be underground, because sometimes our mines are in jungles and places where we can't get permits for our equipment on surface, and you actually are forced to go underground, although that's the last port of call you actually want to do, because it's difficult from a maintenance perspective, accessing it regularly. You have to train your people to go into warm conditions to actually go and work there. So you'd obviously opt for surface installations as far as you possibly can. This is just an example of what a refrigeration system would look like on surface. Some of these refrigeration machines range from 1 megawatts up to 15, even 20 megawatts of installed cooling power that we install. There's also modular type of systems which are mainly used today, which makes for quick turnaround and construction phases. So all those considerations need to be thought through during the planning phase of the mine. We're just going to talk about the services now that we need to ventilate during your planning stages. We're going to talk about, that's both going to cover the caving mines and your sub-level SLCs and block cave mines. So crushers, obviously with crushers, you want to make sure you can basically tip uninterruptedly. So multiple tips. If you can have 4 tipples full, you want to have them full. That's just going to be economical for you from a planning perspective. Obviously, as part of that, you want to ensure that you have no visibility issues. You want to make sure that your main material and your equipment is safe and out of harm's way. And what we typically do from a vent perspective is there's various methods of controlling ventilation and mitigating the dust at these systems. And it could be via just an air ventilation system, an extraction ventilation system, as we see over here. Are they using ducts that extract in your workshop room from the bin out to the return level? Or you can have an extraction system at the tips that actually pull up that dust as the tip, as the LHD operators tip. We've seen designs where people, if they don't have any controls, your LHD driver has to almost tip and go. They don't want to see that throwback. So we've got to consider the dust very carefully. Other places where that we need to consider during ventilation stage is the conveyors. First, we have to think about whether your system is going to be antitropal or homotropal. But what is very important is that your relative velocity between your air and your conveyor is no more than 6 meters a second. Otherwise, significant dust pickup starts. You've got to think whether you're going to just control the dust by using wet scrubbers, dry scrubbers, or ventilation in itself. This is just a typical example, and read too much into the numbers, but what we want to illustrate here is that you can pay almost double for just having a ventilation with air only system as opposed to having a filtration system using dry or wet type of scrubbers. Then the last service is, you have to think about your workshops, your refill bays, your tire bays, your battery bays. All those stations and bays need to be ventilated, ideally directly to return. So those are commitments that you have to provide for, and make sure you provide dedicated ventilation to those districts. Then obviously a strategy that is widely used today is ventilation on demand, where you basically place your ventilation where your producing phases are, and that can actually be based on your mining activities, or you can look at different event-based, or even a combination of them, of how much you can actually produce or provide to those extraction drives or production drifts, depending on the scenarios. Obviously, those controls can be done either by fans or by dampers or by types of valves. but that's a separate design for another phase. Then just quickly through the development phase, during the decline development phase, if you have an example of a twin decline, you sometimes have to ask for additional permission to actually push your ventilation beyond the 6 meters a second that we've spoken about. So typically we'd go to 8 meters a second just to get your phases going, and if you, and to get to, let's say, your first ventilation rise to establish through ventilation to surface. What you then do as soon as you establish your through ventilation, your multi-activity ventilation and mining can actually start. But it's very important to achieve through ventilation as soon as possible during the development phase. This is just an example of showing how important it is to consider and think about how your vehicles and your ducting need to interface. Many times your backs are designed too low and you cannot ventilate, or actually you bump your ducting and you don't provide actually headroom to ventilate these ends. So think about those. The LHDs, you've got to consider jumbos. And then just quickly, what we consider in our design criteria is BEVs, your dust, your heat, and your re-entry periods. Obviously, during the development phase and your producing phases, you want to re-enter as quickly as possible. We then make sure we consider every design criteria during the process. And then what is very important is you have to land in this little sweet spot here where your diesel fumes are diluted, your heat is diluted, your velocity, your blast clearances has been met, and all airborne pollutants are maintained. We're going to skip this slide for today. And then what is very important is then you cycle back to your mine design after considering all these items. And what is very important is to make sure that there's no under or over design of your system. It's energy efficient, it's productive, it's easily maintainable. And then what is very important is that you design a system where every person can go back home after a day's work and know they can have a safe retirement without any health defect. What is very important is to make sure that your employees are safe, and then also that there's profits for your employees and your shareholders altogether. Thanks.
Thank you, Marley. In the interest of time, we'll hold off on questions, so please ask Marley any questions in the break. I'd just like to thank the 6 speakers we've had in this session. It was an excellent session, and we'll recommence at 3:30 for the next following sessions. Thank you.